Okay, we're going to begin talking about correlation now. So many people get confused about correlation, especially because how I teach this class and how it is in most psychology statistics textbooks is that it's after inferential statistics. But correlation is actually descriptive. What it describes is really important. Correlation describes the strength and relationship between two or more variables. We're going to only focus on what's called bivariate correlation. That's only two variables. And this is one that most people are familiar with. Whereas there are multiple regressions and linear regression where we can involve many variables. And in multiple regression, it's kind of fun because you can see the amount of variability that shifts with each added new variable to see where making decisions about how to operate. By gathering more data, finally you get to the law of diminishing returns, and if you add one more data point, one more variable into the multiple regression, it doesn't really help you become any more accurate. Correlation is something that oftentimes people confuse in everyday life. They think that when things are correlated, that means one causes the other. For example, there is a statistically significant correlation between the price of whiskey and a professor's salary. So these two variables, the variability of whiskey, how much it goes up or down, and my salary. Does that mean that I drink so much whiskey that I'm causing, right, a supply and demand curve change in the price of whiskey? No. See, there's this other thing called the third variable problem. There is a statistically significant correlation between how much whiskey costs and how much a professor gets paid. But this third variable explains all of it. It's called inflation. The price of trash removal or a price of a lumber is all related to the price of a professor's salary. It doesn't mean that I throw out so much stuff that I'm changing the market. Inflation is what's causing the variability in all of these things. And so when we take a statistically significant correlation and we think in our minds that that means it causes it, we're missing it. We're missing what it is. There is a relationship between the price of all things and inflation. So whenever you put monetary value or you put it in the hierarchy of monies, its valence is shifting based on the shifts of inflation, not based on the fact that my consumption of something makes other products or services become more or less expensive. So don't confuse correlation with causation. To find if something was causal, what we would have to do is we would have to artificially or experimentally reduce a professor's salary and then watch what happens to the price of whiskey. And if it shifts, then we might be able to make a causal linkage between the two. But if we see that whiskey doesn't change based on shifting my salary, I would say artificially higher, but you could go lower. If you did that and you found that there was no change in whiskey, what you'd see is that my relationship to whiskey isn't one that's causal. It's one where we both share, we co-vary based on another factor, a third variable factor like inflation. We'll continue talking about correlation here in a second. COVID has driven me to drinking. But remember, correlation does not equal causation. If you look at the amount people are drinking now, and you assume that COVID caused them to drink, you might be missing some other factors that particularly are influential in whether or not people self-medicate with anti-anxiolytics like liquor. It might be something else that's coming into play here. So we don't want to take the fact that there's increased consumption of alcohol now during COVID, and therefore COVID causes drinking, right? Like the virus causes you to drink. That's stupid. It doesn't make sense medically or biologically. So no, we don't take those spurious correlations and think of them as something that we should consider causal. Some crazy statistical correlations or relationships between variables have been found. For example, murder by steam, hot vapors, and hot objects is statistically significantly correlated with the age of Miss American contestants. The computer science doctorates awarded in the United States has a statistically significant correlation to total revenue generated by arcades. You've got to be crazy to think that getting a PhD in computer science causes people to spend money at arcades. So what's going on here? See, this is a complicated world, and multiple things have multiple relationships. The amount of variability that is accounted for by one variable solely by another is something that we call R squared, or a correlation coefficient. So let's talk about correlation coefficients. The one that we're going to learn in our class is called Pearsons R. So R is the extent to which two variables occupy the same or opposite positions within their respective distributions. Okay, I know that sounds crazy, but it actually makes sense. Pearsons R is the extent to which two variables occupy the same or opposite positions within their respective distributions. You got two distributions. Let's say height and weight. Can you guys see that? There we go. Height, I gotta close the garage door. I think this will be better. Okay, I've got two respective distributions, right? We've got height and weight. Height and weight, let's say that I'm really tall. I'm 6'2", pretty tall. I weigh 220 pounds, so I'm a little bit heavier than I am tall. But in general, I occupy pretty much the same place within these two respective distributions. If I measured some average person, average weight, they'd probably be average height. If I measured somebody who's really, really skinny or really, really light, they're probably really, really short. Tupac, Biggie, right? Much bigger. And so what we have here is that these two variables co-vary such that your place within the distribution on one of them tells us a lot about your place within the distribution on the other. This is a correlation that will be somewhere near or close to an R value of 1. 1. That is that exactly every single time height goes up 1 notch, weight would go up 1 notch. Perfectly. That's called a perfect correlation. This is the highest correlation you can have, but an R of 1 does not equal causation. Again, you have to have an experimental condition where we see that manipulating only that variable is what causes the other one. No other variability or no other variable could cause any shift in that variable. 1 is a perfect correlation. This, however, -1 is not an imperfect correlation. It's in fact a perfect negative correlation. A negative correlation is something that we'll talk about next. These are the two limits or boundaries of correlation, but they are not opposite of one another, strangely. 0 is the opposite of 1 and -1 with regard to correlation. That is, again, the extent to which the two variables, we're doing bivariate correlation, occupy the same place is 0. There's no, it's complete randomness. If you knew one variable, you would know nothing about the variability of the other variable. So, a negative correlation. How about number of hours studied? That's this distribution. And grade on test. That's this distribution. Look, for the most part, if you're somebody who's studying more hours compared to all your peers, guess what your grade is? Probably here. But watch if I change this. This would be a positive correlation. Watch if I change it to errors on test. If you are the one who's studied so much, do you think you're going to have the most errors in your distribution? No. You're going to probably have some of the least. Okay? If you're here, where you're higher than average, you'll probably have less than average errors on the test. You see, this is a negative correlation. Negative correlation means that as x, this would be labeled x, this would be labeled y. As x increases, y tends to decrease. So, negative correlation doesn't mean bad. In fact, if you study more hours, you get less errors on the test. That's a good thing. So, negative correlation doesn't mean bad. It just means that as one of the variables goes up, the other one tends to come down. We're back, and we're going to learn how to calculate Pearsons R. So Pearsons R, as we talked about, is equal to the extent to which these two variables occupy the same or opposite positions within their distribution. Now, I'm going to show you the formula first, just because you know all of this stuff. Okay? You know all of this stuff. So R, make a good one. R is equal to the sigma sum of zx times zy, that's called a cross product, divided by n. This is the formula. What does it mean? Well, you're going to have to calculate the z for all of x, that's the first variable that we measure, say height in the height and weight one, or say professor salary in the professor salary and whiskey one. You're going to calculate the variability, right? So you get the mean and standard deviation, because if you remember how to calculate a z-score, z is equal to x minus mean divided by standard deviation. So we do that to figure out what each of the z-scores for x are, and each z-score is going to have a corresponding, each z-score for x will have a corresponding y-score. And again, those are comparing the x scores to all of their place in their distribution, and all the y scores to all the y place in their distribution. When we do cross products, that's zx times yz, then we're going to find that we add them up and divide by how many of them there were. This gives us Pearsons R, or that number between 1 and -1. Remember, 0 is the opposite of 1 and -1 in this scenario. That describes the numeric value of the extent to which these two variables occupy the same or opposite places within their respective distributions. For those of you that don't like z-scores, you want to do another one. I like that z-score equation. It seems to me to be the easiest. But if you want a different r-squared equation, super easy. You ready? You take the sum of x minus the mean of x, that's so all values of x minus the mean of x, times y minus the mean for y, which is each individual score of y subtracted by the mean. Okay, you take that, and then you divide that by the square root of the sum of squares for x times the sum of squares for y. You'll get the same answer as if you do that z one. So again, if you're interested in calculations, this could be your friend. You don't want to calculate all those z-scores and do the cross products. Just calculate sum of squares, means, y. This should be easy. You'll get the exact same number for r you would if you did that other equation. I think the other one's way easier. Okay, we're going to be talking about r squared now. So r squared is basically just the r, the Pearsons R. Carl Pearson was the one that invented the R statistic. It's r times itself. And that seems pretty easy. If you have a correlation of, say, 0.5, then 0.5 times 0.5 would be 0.25. So you've got a quarter, right? So if you had a correlation that was 0.5, r squared would be 0.25. Okay, Google, what's 0.5 times 0.5?
The answer is 25.
Nope. Okay, Google, what is 0.5 times 0.5?
The answer is 0.25.
You guys can't see that. I don't know why. It's right here. Anyway, it says 0.25. What that means is a quarter of the variance that we see in one variable is explained solely by that other variable. If we had something like height and weight, and they had a correlation of 0.5, That means that 25% of all variability in height would be explained by weight alone. So this is a way that if we continue to load up models, you can see that if I wanted to figure out what was someone's height and I added up not only their weight, but their age, their parents' height, other variables that have explanatory relationships with height, then I'd continue to get better and better at reducing the error I had in predicting someone's height if I knew all that other information about them. This is what Amazon and Google and Facebook and Twitter and Insta all use to get information about you and then to predict your behavior, to predict what they want to sell you, what they want to show you, what they want to restrict you from seeing. So this is the algorithms that's used as multiple regression models to figure out your behavior. So if I bought Expo markers on Amazon the other day because I'm running out and I can't go to work because, well, they won't let me go to work. I have to work here in my garage. Amazon now has a knowledge about how often I buy these. They also know how often these last, another variable. And they also know where I work. Not because I tell Amazon, but because they know everything. All those variables they can continue to add into models to predict what I might want other than just Expo markers. And they sold it to me, the Expo eraser. See? They've continued to add variable after variable to predict or to lessen the error in their prediction of what I will buy next. And finally, Expo whiteboard care. See, they got me hook, line, and sinker. With all the data, they figured out what I wanted and they continued to push that to me by taking the variables of knowing that I purchased a whiteboard on Amazon, I purchased Expo markers, I purchased Expo eraser. They're like, you're at some point going to need to wash the whole thing down. So why don't you buy this product that you'll use for the product we know you already bought? They're reducing their error. They didn't send me, hey, looks like you need an oil filter for your car. Why do I never get oil filters for my car? You probably know this. You saw it in that other video. It's an electric car. There's no oil to be changed in it. So Amazon knows that about me, and then they don't make the error of sending me an oil filter ad. That's what we can do with continued correlation. The more correlations we can find, the less error we can make in predicting. And that's where we'll come into scatter plots. We want to create a scatter plot. A scatter plot is a way to demonstrate and to visualize the relationship between two variables that is otherwise in a correlation coefficient a little bit difficult to conceptualize. What we'll do is we'll use x and y not only as the variables but as the axes that we draw these upon. So let's say we use the data that's in the book about x and y for happy mood and sleep. So we'll have, let's say, hours slept will be on the y, or the vertical axis, and happy mood will be on the x-axis. Now what do? We're going to take each of these and we'll figure out, well, what are the ranges? Okay, so for happy mood, we had ranges between, I think 2 is the lowest and 7's the highest. So what should we display? I think a 0 to 10 scale makes perfect sense to give you a sense that there's nobody on the super depressed and there's nobody on like the, elated ecstasy and nirvana scale, that there's people in between those. So in the middle would be 5, 6, 7, 8, 9, and 4, 3, 2, 1. So we've made our scale approximate to the data that we have and we want to display. Same thing we're going to do again for hours slept. We had nobody that slept 0 hours sleep, but maybe we want to put on there the max. The max that we had was 10 hours slept. 10, 9, 8, 7, 6, 5. So nobody slept less than 5 hours, and nobody slept 0 hours. So I'm going to restrict it just to the range. You could do either. Doesn't matter. But you see that I scaled it appropriate to the data. So for the first person, they had a 7 hours slept and 4 happy mood. So we go 7, 4. Okay, there's that one. I've done that by finding 4, that person's particular mood rating, and 7, that particular person's hours slept, and triangulating upon them to find where I will place my marker. This marker denotes both 7 hours slept, 4 happy mood. Next person, 5 hours slept, 2 happy mood. So 5 hours, 2 happy, right there. So we've got 2 hours slept, 5 happy mood. I'm going to erase these just because I don't think you need them. I'm pretty sure that you understand what I'm doing in terms of graphing this. I did want to show you that that's how I figure out where these dots go, is that I go to the one, I go to their y, and then I go to their x variable. Okay, next one is 8 hours slept and 7 happy mood. So 8 hours slept, and then I go over to 7 happy mood. See that? Right there, right there. And then the next one is 6 hours slept, 2 happy mood. 6 hours slept, 2 happy mood. The next one is 6 hours slept, 3 happy mood. See, it's right next to it. And the next one is 10 hours slept and a 6 happy mood. So I go up to 6 and 10. I find it right there. Now this displays the relationship between hours slept and happy mood very well because it's showing that there is a trend or a relationship that as one goes, so goes the other. This is called a positive correlation. Now why is it positive? Positive because the extent to which these two occupy the same places in their respective distributions happens to be that they're in the same position, not in the opposite positions. If they were in the opposite, then what you would see is a different trend. And we'll get to that in a second, a negative correlation. But here's what I want to talk about, is a line drawn through them. Now, if I were to draw a line that minimized the distance between itself and all of these dots at one time, I could figure that out mathematically. Again, the error is going to be like this. And what this does is it minimizes the distance between those dots and that error line. This is called the least squares regression line. Why is it called the least squares regression line? If you square the distances between those dots and this particular line, it will be the smallest number possible. So that's a minimum. And that minimum is how this line is actually formulated. So the least squares regression line. Great news about it. It tells us there is a trend that the more hours slept, the happier the mood. This is a general trend that gives us that sense of, if we're going to include this in a multiple regression, we would try to increase knowing how someone's happy mood would be by knowing what the hours that they slept the last night was. So this is how linear regression, correlation all come together, is in scatter plots. The x and the y variable showing that trend of correlations. Now, what types of correlations, what types of scatter plots can there be? We'll get to that next. We're back with types of scatter plots. Scatter plots can show us the kind of relationship that these two variables have. The first one that we saw was one that all those dots kind of really hovered really tightly right around that line. This type of relationship is called a linear relationship, and this is a high positive correlation between the value of y and x. That's not what all relationships are like. For example, there's a classic relationship called the Yerkes-Dodson curve. If you check out the Yerkes-Dodson curve, you'll find that it plots arousal. I'll plot it this way. Performance versus arousal. Now, arousal just means how awake you are. It doesn't mean like you're aroused. It just means that you're awake, not asleep. The more aroused you are, the more level of stress. Another way you could put this would be stress. Right? When you're asleep, you're at zero stress. So there's no stress happening for you at zero sleep. Arousal, stress, same. Performance. Anything that requires you to perform a task, a behavior, whether it be reciting the Gettysburg Address or performing on a math test or going to on a date. Or do you date anymore? Is that what you guys do, or you just swipe each other? Just a swipe, and then that's something. I don't know. I don't understand things. But your performance could be on something like a job interview or the final exam in this class. So what Yerkes Dodson, here, I'll write it here. Yerkes Dodson. The Yerkes Dodson curve suggests that as we increase arousal, we actually increase performance. So if I went to give you the final for this test, the final test for this class, and I woke you up in your bedroom in the morning when you had just woken up, you're at the lowest level of arousal. There's zero stress in your mind. You're just woken up, right? You haven't, it's creepy that I'm in your room, but whatever. You have no arousal. So as you increase your arousal, if I gave you the test right then, you'd fail. You'd have a very low performance. But if you got up and ate some breakfast, maybe did some exercise, went for a walk, reviewed your notes, did some breathing exercises, you would increase your performance to its max level. However, this is not a linear relationship because that's only halfway to stress. If, on the other hand, you start to catastrophize and ruminate and consider all the possibilities, if I don't pass this final, then I might fail the class. If I fail this class, I'm not going to graduate. And if I don't graduate, I'm not going to get a job. If I don't get a job, I'll not have a career. If I don't have a career, I won't have a life, and I won't have a husband or a wife, and I won't have kids, and I won't have a family who loves me. I'll be living alone with all these cats. And look where we are again at performance. Performance is low, but stress is high. This relationship between stress and performance, the Yerkes-Dodson curve, is best described instead of a linear relationship as a curvilinear relationship. Something really good to remember. This is the zone that you want to be in, right there. You want to be in that zone because your optimal level of arousal and your optimal level of performance. Sometimes you want to be just here, just a little bit beyond it, so that you know you can go back. And if you reduce that stress, you won't have this direct relationship between performance and stress as a curvilinear relationship. You'll have a more direct sort of look at things as if I increase my stress to this peak level and I know what that is, then that relationship is a linear relationship. So that is the Yerkes-Dodson curve. That might be the most important thing I've ever taught you. Okay, types of scatter plots. We have that is a high positive correlation. High positive. If there's clearly a trend, but those dots are separated more, the further apart those dots separate from the least squares regression line, the smaller the correlation coefficient will be, and we call these low positive correlations. Now there is other kinds of correlations. For example, what if you saw this data that looked like this? Where do you draw the line through that? Mathematically, we can draw a line through this. Right? There is a line somewhere that will minimize the distance between every single dot here on the chart, which represents two variables, both the y and the x, and it minimizes the distance from all other lines that could be drawn. If we treat this like this was somehow a linear relationship, we could fudge a line in here that doesn't really make sense, but it's not going to be helpful in understanding the relationship between x and y. For example, if you see this, there is no relationship between x and y. This is no correlation. Okay? No correlation. Now we come to negative correlations. If I say, ask the question of, how attractive you are on the y-axis, and I wanted to plot on it Number of months that pass without getting a date. No. I'll say number of rejections that you have. No, that won't work either because that'll be a positive relationship. How about this? Negative correlation between, we already gave this one, but I'll do it again. Hours studied and errors on test. So, the number of hours studied, as it goes up, what tends to happen to the errors on the test? They tend to decline, right? So here are errors on a test. Here's, let's say, 100% of your answers were errors. Hours studied to errors on the test, it looks like this. If you studied 0 hours, you're going to be answering at chance level. You're going to have really low level of performance. And we have a high negative relationship. This is a high negative correlation. There might be another one like the years you spent in school and the time you spend unemployed. So here's education in years, right? Nobody does more than 16, but unless you're like me, if you stay around, they just eventually start paying you. Here's 0. And here's, let's say, months unemployed. What we would find is that people who have high levels of education tend to have less time unemployed. Now, generally speaking, this is a downward trend, and this shows that these spread out dots show that there's definitely a relationship here, but it's not a strong relationship. We would call this a low negative correlation. So there's high positive correlations where all the dots squeeze around a line going from the bottom left to the upper right. There's a low positive correlation where there's definitely a trend of X and Y both going up together, but those dots are spread out farther apart. There's a high negative where there's a direct relationship between as X increases, Y tends to decrease, and the dots are squeezed around it together really tightly. Or like this one, as X increases, Y tends to decrease, but these dots are spread out more than that. And then also there's that possibility that you look at it and it's just all over the place, and we have not low, but we have no correlation, right? Where again, we drew a line just because you can mathematically, but that might be like no correlation. So those are the different types of scatter plots that indicate the magnitude and direction of the relationship. The correlation coefficient tells the extent to which these two variables occupy the same place, and if they occupy almost the same place, the correlation will be high towards 1 or -1. If they don't occupy the same place, if it's a low correlation, they'll be closer to 0. And you can also run a t-test to find out if there's a statistically significant correlation between them, which is the one that you would not find just chance, thrown two variables together. And so we'll look at that statistical way to find if a correlation is a statistically significant one or if it's a spurious one that we don't need to counter. We're back. If you want to do a t-statistic, a t obtains... That light is bothering me, hold on. Mucho mejor. Okay, if you want to do a t obtained statistic on a Pearsons R, you do it like this. The t obtained, and again we'll compare this to a t critical with an n minus 2 for the degrees of freedom. So just regular t. This is the statistic is R. So whatever we got for our Pearsons R, then we're going to take divided by the square root of, and this will be 1 minus R squared times n minus 2. So if we do this, this will give us a t obtained value. And then that t obtained value will compare to our t critical value with the degree of freedom as n minus 2. Why is it minus 2? Because we have an x and a y variable. So there you go. That's how you run a significance test on a Pearsons R correlation.